The mission team is making sure the robotic scientist, now in its fourth extended mission, is staying strong despite wear and tear from its 11-year journey. For 1,000 Martian days after setting its wheels in Gale Crater on August 5, 2012, NASA's Curiosity rover remains busy conducting exciting science. The rover recently drilled its 39th sample, then dropped the pulverized rock into its belly for detailed analysis to study whether ancient Mars had the conditions to support microbial life. The rover has been gradually ascending the base of 3-mile-tall, 5-kilometer-tall Mount Sharp, whose layers formed in different periods of Martian history and offer a record of how the planet's climate changed over time. The latest sample was collected from a target nicknamed Sequoia. All of the mission's current science targets are named after locations in California's Sierra Nevada. Scientists hope the sample will reveal more about how the climate and habitability of Mars evolved, as this region became enriched in sulfates, minerals that likely formed in salty water that was evaporating as Mars first began drying up billions of years ago. Eventually, Mars liquid water disappeared for good. The types of sulfate and carbonate minerals that Curiosity's instruments have identified in the last year help us understand what Mars was like so long ago. We've been anticipating these results for decades, and now Sequoia will tell us even more, said Ashwin Vasavada, Curiosity's project scientist at NASA's Jet Propulsion Laboratory in Southern California, which leads the mission. Deciphering the clues to Mars' ancient climate requires detective work. In a recent paper published in the Journal of Geophysical Research, Planets, team members used data from Curiosity's chemistry and mineralogy Shaman instrument to discover a magnesium sulfate mineral called starkite, which is associated with especially dry climates like Mars' modern climate. The team believes that after sulfate minerals first formed in salty water that was evaporated billions of years ago, these minerals transformed into starkite as the climate continued drying to its present state. Findings like this refine scientists' understanding of how the Mars of today came to be. Time-tested rover. Despite having driven almost 20 miles 30 kilometers through a punishingly cold environment bathed in dust and radiation since 2012, Curiosity remains strong. Engineers are currently working to resolve an issue with one of the rover's main eyes, the 34mm focal length left camera of the mast camera or mast cam instrument, in addition to providing color images of the rover's surroundings. Each of mast cams to cameras helps scientists determine from afar the composition of rocks by the wavelengths of light or spectra they reflect in different colors. To do that, mast cam relies on filters arranged on a wheel that rotates under each camera's lens. Since September 19th, the left camera's filter wheel has been stuck between filter positions, the effects of which can be seen on the mission's raw or unprocessed images. The mission continues to gradually nudge the filter wheel back toward its standard setting. If unable to nudge it back all the way, the mission would rely on the higher resolution 100mm focal length right mast cam as the primary color imaging system as a result. How the team scouts for science targets and rover routes would be affected. The right camera needs to take 9 times more images than the left to cover the same area. The teams also would have a degraded ability to observe the detailed color spectra of rocks from afar, along with efforts to nudge the filter back. Mission engineers continue to closely monitor the performance of the rover's nuclear power source and expect it will provide enough energy to operate for many more years. They have also found ways to overcome challenges from wear on the rover's drill system. Robotic arm joints software updates have fixed bugs and added new capabilities to Curiosity, too, making long drives easier for the rover and reducing wheel wear that comes from steering. An earlier edition of a traction control algorithm also helps reduce wheel wear from driving over sharp rocks. Meanwhile, the team is preparing for a break of several weeks in November. Mars is about to disappear behind the Sun, a phenomenon known as solar conjunction. Plasma from the Sun can interact with radio waves, potentially interfering with commands during this time. Engineers are leaving Curiosity with a to-do list from November 6th to 28th, after which period communications can safely resume. More about the mission. Curiosity was built by NASA's Jet Propulsion Laboratory, which is managed by Caltech in Pasadena, California. JPL leads the mission on behalf of NASA's Science Mission Directorate in Washington. Mellon Space Science Systems in San Diego built and operates Mastcam. While most of our contact and remote observations are specific to the parking spot on a given Sol, REMS and RAD observations care less about where than when. Sophia and Jorge from REMS, and Bent and Carrie from RAD work with the environmental theme group to make sure their instruments take measurements at regular intervals, Sol in and Sol out, to produce unbroken records of the Martian environment. Dan cares about both where and when. So Dan team members like Dennis and David make sure Dan actively pings the subsurface and back of the rover as soon as we arrive at a new parking spot, and then subsequently gathers passive data as we sit for contact and remote science. Shaman and SAM use are not a daily or even weekly occurrence, but when it is time to collect a drill sample or measure methane in the atmosphere, their teams stand at the ready. Shaman team members like Liz and Patricia and SAM team members like Genevieve and Christine make sure that their instruments are ready to receive sample, and then work with their teams to analyze the data as quickly as possible to reveal to the whole science team what Martian secrets have been revealed. As you can see, it takes an amazing, dedicated team of people, only a small handful who I could highlight, to make one Sol of Curiosity observations a reality. If the people above are the engine that makes Curiosity go, then the fuel is our project science leaders, Ashwin and Abigail. They lead by example, often serving in many of the roles listed above, and form this diverse group of scientists and engineers with many ambitions into one team with one goal, moving ever forward to new discoveries. Come back at the end of this month to see where we take Curiosity next. Earth planning date, Wednesday, November 1st, 2023. Today we begin the final countdown into Mars' solar conjunction, when Mars is effectively on the other side of the Sun and we can't reliably communicate with Curiosity. Only 2 more planning sessions after today. In these final days before conjunction, we begin reducing the types of activities we allow in our plans, because we do not want to risk having a fault that we do not have time to address. This plan would be our last chance to do full contact science, but since we have sample in the drill, we actually can't point other instruments at the ground. We also don't have a lot of power to play with, as Curiosity is still recovering from the SAM analysis we did in the prior plan. As a result, our drill campaign is now on hold and we are focusing on imaging today. On the first Sol of our 2-Sol plan, we have about an hour of imaging, beginning with a navcam image of the open SAM inlet cover. We do this after each sample drop-off to make sure we don't see a lot of spilled sample around the inlet. We couldn't do this after the drop-off in the last plan because it was too late to get good lighting. After that, Mastcam is doing some additional testing on the filter wheel and taking a 10x6 mosaic of the Sequoia workspace. Next, Chemcam is taking a 5-spot mosaic of Aperture Peak, which is a ridge that appears to be made of vein material. After a nap, we kick off a SAM monthly maintenance activity. The next morning, Curiosity wakes up for some additional imaging. The morning activities include several atmospheric observations, looking for dust and clouds that might for this time of year. This includes a Mastcam Solar Tau, Navcam Superhorizon movie, and a large Navcam Dust Devil survey. Chemcam also takes to long-distance mosaics. A 10-frame one looking uphill at the upper Geddes Vallis Ridge and a 7-frame one looking across the crater at the Peace Vallis Channel near the crater wall. Mastcam finishes up the morning block by imaging Bench Lake, which is a bedrock feature with a distinctive texture, and taking a post-Chemcam look at Aperture Peak after a long nap. Curiosity wakes up for some late afternoon observations, including a set of Navcam sky flats, looking for dust features on the lenses, and a set of Twilight movies looking for clouds, while we did not get any new images from the last plan. This image of the crater rim is similar to the one in today's plan, and we'll be able to compare to see how the dust in the atmosphere is changing. Curiosity rover captured its highest resolution panorama yet of the Martian surface between November 24 and December 1, 2019. A version without the rover contains nearly 1.8 billion pixels. A version with the rover contains nearly 650 million pixels. Both versions are composed of more than 1,000 images that were carefully assembled over the following months. The rover's mast camera, or mast cam, used its telephoto lens to produce the panorama and relied on its medium-angle lens to produce a lower-resolution panorama that includes the rover's deck and robotic arm. Mellon Space Science Systems in San Diego built and operates MastCam, a division of Caltech. NASA's Jet Propulsion Laboratory manages the Mars Science Laboratory mission for the agency's Science Mission Directorate in Washington and built the Curiosity rover. This wide view of the John Klein location selected for the first rock drilling by NASA's Mars rover Curiosity is a mosaic taken by Curiosity's right mast camera mast cam during the afternoon of the 153rd Martian day, or SOL, of the rover's work on Mars. Veins interpreted as evidence of a wet past are common in the flat-lying rocks of the area. An excerpt from this scene provides an indication of scale. This mosaic of telephoto images has been wiped, balanced to show what the rocks would look like if they were on Earth. A raw color version is also available, showing what the rocks look like on Mars to the camera. Mars is the fourth planet and the furthest terrestrial planet from the Sun. The reddish color of its surface is due to finely grained iron 3 oxide dust in the soil, giving it the nickname the Red Planet. 2122, Mars's radius is second smallest among the planets in the solar system at 3,389.5 kilometers to 106 miles. The Martian dichotomy is visible on the surface on average. The terrain on Mars's northern hemisphere is flatter and lower than its southern hemisphere. Mars has a thin atmosphere made primarily of carbon dioxide, and to irregularly shaped natural satellites, Phobos and Deimos. Geologically, Mars is fairly active, with dust devils sweeping across the landscape and Marsquake's Martian analog.